In previous videos, we've looked at what it means to have a better test, how to compare tests. And in this video, we'll start to think about how we might understand how to derive a most powerful test. And we'll start out with the Neyman-Pearson Lemma. And this will help us work on cases that are a bit more complicated. But we're starting out with a simple versus simple hypothesis test. So that means the null hypothesis is simple and the alternative is simple. So basically, the parameter of interest is equal to something under the null versus it being equal to something else under the alternative. So we'll use the notation that L of theta given x is our likelihood function for the IID sample, a vector of x's. And we'll let C denote a rejection region or a critical region of size alpha, and k is just a non-negative real number. So we'll say if there exists a rejection region C of size alpha and a k greater than or equal to 0, such that a ratio of likelihood functions, so the ratio of the likelihood function under the null divided by the likelihood evaluated under the alternative, if this ratio is less than or equal to k for x in the critical region, then this critical region C is the best critical region of size alpha. And sometimes this ratio, you could call it a likelihood ratio, is denoted lambda. It's a function of x, and then our parameters theta naught and theta 1. So the idea behind the Neyman-Pearson Lemma is really what we've described as a mathematical way to put points into the critical region until it reaches size alpha. And in order to maximize the power of the test, points that are more likely under the alternative than under the null would be put into the critical region. And so that seems to make some intuitive sense. If points are more likely under the alternative, then you would like to reject samples that look like that. And if you think about how this is working, if you have a sample that is more likely under the alternative than under the null, then the denominator of what we called lambda, that likelihood ratio, is larger, and so that lambda is smaller. So the denominator of lambda being larger makes the entire lambda smaller. So this is where we get the requirement of putting points into C of the form lambda less than or equal to k. So let's look at an example to build up our intuition. So suppose we have an IID sample from a normal distribution with a known variance, and we want to test some claims about the mean of the normal distribution. And in particular, we want to test the null hypothesis that mu is equal to 1 versus the alternative that mu is equal to 3. Now, the Neyman-Pearson Lemma says to take a look at lambda of the data where we have theta naught equal to 1 and theta 1 equal to 3. And what happens here is we have the likelihood evaluated at 1 over the likelihood evaluated at 3. And really what that's equal to is the joint PDF where we plug in mu is equal to 1 divided by the joint PDF where mu is equal to 3. And we want this under the Neyman-Pearson Lemma to be less than or equal to some value k for our sample points falling in the critical region. So what this says here is basically something like lambda should be small for points in the critical region. Well, let's think about what that would mean visually. So suppose we had our distribution under the null. And so this curve here, let me highlight, this is the distribution under the null hypothesis. So here we're centered at 1. And then I'll draw the same curve, but centered at 3, so the likelihood under the alternative. And we'll have, say, centered at 3. And maybe we'll highlight this one in green. And what we're trying to do here is figure out where we can place C, which is the boundary of our critical region. So we're going to think about a critical region as just an interval along the real line. And it seems like, some reasonable choices for C. Well, C has to be placed somewhere such that the area under the curve and over the critical region is alpha, because we want a test of size alpha. So we could do this in different ways. So here's maybe a bad way to do it. Imagine we chose a boundary C here, and then we chose our critical region to be out here, and what might allow us to do that is that this area here is alpha. This meets the criterion that the area under the curve is alpha, so this critical region has probability under the null being alpha, so that meets the desire that we have a test of size alpha. But the reason why this critical region won't be chosen by this likelihood ratio is because in this case, if we drew this curve out further, we'd basically be getting a very, very, very small likelihood, which means the denominator of lambda would be very small compared to the curve here for in the numerator, which is the curve, the likelihood under the null. So we would have a likelihood ratio that's very large as opposed to something that's being small, right? This Neyman-Pearson Lemma says that ratio should be small. So of course, that was a bad choice. So what do you think would be a better choice? Right? Intuition says, well, probably on this side. If we chose it over here, so here's our boundary point C, and here is our critical region, and this is chosen such that the area here is alpha. This seems better because this critical region allows for points falling inside of it to have a small likelihood ratio, meaning this green is above the purple, so the alternative likelihood is greater than the null likelihood, and so the ratio works out in the way we would expect. And of course, this should all match our intuition, right? What we're sort of showing here is that the Neyman-Pearson lemma matches our intuition, which says that we should reject if we get sample means, larger than, in the upper tail rather than the lower tail. If you got a sample mean down here, that doesn't seem like it would be good evidence for the alternative hypothesis, which is that mu is equal to 3. So our intuition says we should reject when we get a sample mean that's high, and the Neyman-Pearson lemma gives us that based on this likelihood ratio. So in the next video, we'll take a look at a similar example where we actually go through the math.